Okay, the last topic that's in the second unit is going to try and tie a bunch of things together in this application. So here what we're looking for is the shortest distance from a point to a line, and we're going to just kind of look at a scenario first to figure out how we're going to need to do this. So here they've given us some point, some line. They've asked us to investigate if we wanted to connect the given line to the given point with some kind of line segment, what is the shortest line segment that we could use? Okay, so imagine something like this happening. Let's say, for example, and I'll choose a really bad one to start. Let's say I say this. I'm now connecting that line, to the point with this line segment. Is this the shortest one I could possibly make? Well, no, because I could do this one too, right? Let's say I do this. Well, that line segment definitely looks smaller than that line segment, so this one should be shorter, and I could just kind of say, well, that's still not even the best one, because maybe I could do this. Let's make one that's like that. And I could keep going this way, so that this one, yeah, it kind of looks shorter than that one. It's definitely shorter than that one. Can I improve on this? And I can keep going, but how do I know when I've gotten kind of the best possible line segment chosen? Well, let's see if my eraser works now. I need to find a better one. Garbage. What I could do is use the idea of Pythagorean theorem. Because what Pythagorean theorem says, if I have this, then if this is at a right angle, then this is now the hypotenuse, and I know that the hypotenuse is always the longest side in the triangle. So think of it like this. In terms of this length to this length, this is connecting the point to the line. So is this. This is connecting the point to the line. But because this is the hypotenuse, this is guaranteed to be longer. So this one's already shorter. And if I had used any of those other ones that didn't erase well, so let's say I put that one back, then here I've now made another one of these right triangles. So I've got Pythagorean theorem going all over again, saying that here I've connected the line this way, but I've also connected the point to the line this way. Which one's shorter? It's guaranteed to be this one, because that's now a hypotenuse. And the hypotenuse is always the longest side. So this one is guaranteed to be longer than that. And I can keep going with this almost infinitely. That here's another possible hypotenuse that's there. That's going through the really bad erased part of the page. But I've got another right triangle. And this is connecting the point to the line, but it's a hypotenuse. So this is automatically longer than that. Which then, if you kind of see where I'm going with this line segment right here, this is guaranteed to be the shortest one. It's always going to be perpendicular to this line. So this is the one that we're going to have to try and find. This is guaranteed to be the shortest line segment. Because no matter what other type of line segment I create connecting this point to that line, compared to this one, I could make a right angle triangle, and then that other line segment would be a hypotenuse in the right triangle, meaning that it's longer than this line. So if I want to connect a point to a line segment, I'm always connecting it using this line segment that's perpendicular to the line that I'm connecting it to. So that's what we're going to try and do. And we've got a process that we're going to have to try and follow. And I will not go through the process kind of step by step. I'm going to do it in an example because that's usually the best way to do these things. So here it says, determine the shortest distance from this point P, which is at -4, 6. So let me put that in. Here's -4, 6. There's my point P. And it's connecting to this line. Well, the way that line is written, that's standard form, which is fine. But if I want to draw it, it's usually better if I just convert this. So let's rewrite this. We'll move the y to the other side so that it's positive. So there it's in the y equals mx plus b, so I could draw this line. So this is one that has a y-intercept at -1 and a slope of 2. So up to right across 1 for each of these. Okay, so let's do that. Let's just draw this in. Hopefully that shows up good. Okay, so then this is our scenario. I want to know, how close does this point get to this line? What is the shortest distance that it's going to be able to be made between this point and this line? Well, based on what we kind of investigated above, then what I'm going to need to do, let me rotate this a little bit because maybe it'll be easier there, is I'm going to try and connect this with some line segment that's perpendicular to this line, but that goes through this point. So I'm going to try and find that line segment. That's going to look something like this. Now, once I have that line segment, if I want to get the shortest distance, then what I'm going to have to do is find a point of intersection. Where does the line segment that I'm making actually connect to this line? And then once I've found that, then I can actually calculate the distance, because we have, at the very beginning of this unit, a formula for calculating the distance between 2 points. So that's kind of my 3-step process that was written up here. First, I'm going to find the equation of the line segment that's going to be perpendicular here. Then I'm going to find, where does that actually meet? Where do they intersect somewhere here? So that I could use the distance formula between this point and the point of intersection, and then calculate the distance. That'll be our shortest distance. Okay, so let's go through that in those steps. So let's do step 1. We need to get the equation of our line. Okay, so to get the equation of this little kind of line segment that's here, I need the slope and I need the y-intercept. So what I could do is, let's say, do this. Here, let's find equation of the perpendicular line segment. Okay, to do that, I'm going to need the slope. Here, I already know this is a slope of 2, which means that the slope we're going to need is going to need to be a negative reciprocal. It has to be perpendicular. So if this one has a slope of 2, because that's what the line had that was given to us, then the slope that we're going to use is going to have a slope that is negative 1 over 2. Because I'm taking, again, this is a slope of 2, I need to be perpendicular, so negative reciprocal. So that's going to be our slope. As soon as I have that, then let's get the y-intercept. And to get the y-intercept, let me make that a little bit more formal, then I can use the y equals mx plus b and start plugging things in. I now know the slope I want, so there's my m, and then the point that's going to be going through this, the only one I know is p. These ones that are along this line, I don't know exactly which points are going to go through it yet. So let's plug in p, which is negative 4 and 6, and we'll solve for b. Okay, so let's see what's going to happen. I've got a 6 equals a 2 plus b. So I've got here b being 4, which means that the equation that I need to use is y equals slope x plus b. Okay, so that is going to be the line segment's equation. So I could even put that in right now, because now I know that it's going to be going through the y-axis at 4 and has a slope of negative 1 over 2. So 1 down, 2, okay, so right here. Which means this is the actual line segment we want. It's the one that connects P up to that point that I just happened to plug in. Okay, so that is going to be our line segment. So I need the shortest distance of these things, or between these 2 points. Now, if I'm not always going to be able to draw this, so let's try and figure out an analytic way of doing this. Now that I've got this line segment equation, and I have this line that was given to me, if I want to know where they meet, then I'm finding the point of intersection. I'm solving a system, which is step 2. Okay, so let's solve that system. So we've got this line segment that we just got, y equals negative 1 over 2 x plus 4, and the one that was given to us already that we just rewrote. So now I've got this line's equation, I've got this line's equation, I'm looking for this point, which I can kind of see on the diagram. But if I didn't have a diagram, I could do this algebraically, and then we can solve this using substitution that's here. So let's put these two things together. So 2x minus 1 equals negative 1 over 2x plus 4. And then if you don't like working with the denominator, then clear the denominator by multiplying everything through by 2. And let's solve for x. So let's move all the x's over here. Everything that's not an x will move on this side. So I've got 5x equals 10, so x equals 2. Okay, so where they're going to meet is when x is a 2, but I also need the y coordinate, so plug it into either one of these. Let's say I plug it into that one over there, then y is 2 times whatever x is minus 1. Y is a 3. Okay, which is exactly what we have here. They're meeting at 2, 3. So that's going to be where their point of intersection is. And then the last thing, because I'm trying to get the shortest distance, is now that I know exactly where these 2 points are, they already told me this one, I just found this one. If I want to get the shortest distance, use distance formula now. So let's do step 3 over here. I got a little bit of space, so I'm going to calculate the distance. Okay, and our distance formula again was this reworking of Pythagorean theorem. And then I'm getting the difference in x's. Let's say we'll use this point here. So that's its x coordinate, that's its y coordinate. And then we're subtracting from that another point, and the point we're going to use is point P. So that's its x, that's its y. So this is going to be the root of 6 squared plus negative 3 squared. So I've got this square root then going on here of whatever 36 plus 9 is. So this is the shortest distance between that point P and this line. The closest they get is root 45, whatever that is, units long. And I'll keep that exact. And then we don't know the units, so I'll just say units. It's root 45 units. Okay. Now you might be wondering, like, where are we going to use this stuff? Well, you can think of it in terms of like triangles, because what this could actually be used for, and if I tilt this a little bit over here, is because what I did with the shortest distance here is I found this line segment that was perpendicular to the side that was right across from that point P. Then if you think of it with a triangle, then what I actually did, if you kind of draw this imaginary triangle that's here, is I actually found its altitude, I found its height. Because if you think of this as being a vertex of a triangle, and I want to know exactly how high that triangle is, then it's going to be using an altitude, which is that line segment that is perpendicular to the other side. And when we found altitudes, all we did was found the equation, which is essentially what we did here. But if I want to actually find the length of the altitude, the height of the triangle, then I need to know exactly where that line segment intersected the other side, which is what we did here, and then find the actual distance between those 2 points, which is what we did here. So we can use this process to find heights of triangles. And heights of triangles can be used in a lot of things, finding the areas of triangles and I don't know, applications referring to those things.